we are continuing our foray into this discrete event idea. And today we're going to start on this thing called event graphs, which are going to be one of the primary mechanisms by which we design discrete event simulation models. This is a very simple and yet very powerful way to describe these models. It describes them in ways that other characterizations don't. So for example, in your other classes, you may have encountered things like, well, between things like flowcharts, which are, again, a graphic representation of a process. You may have encountered something like finite state machines, which again bear a superficial resemblance in the way they look to event graphs, and yet have entirely different meanings. So if you have any any experience with any of these other approaches, for these purposes, at least for our time together, it would probably be useful to just kind of put that aside and focus on what we talk about here. So today we're going to talk about event graph methodology. Again, this is in the reading. And as you know, there's very short reading because you can describe this very quickly. There really isn't a lot of complexity to it. There is some. That is, we are going to first deal with the simplest version of this. And it turns out that there are some additional features, not that many, but there are some additional features that just simply facilitate building models that in a fairly straightforward manner. Okay, we're going to look at a couple of examples. We're going to redo the two examples we did yesterday, the arrival process and the multiple server queue. And then we're going to engage in the start of an iterative process for modeling. This is something that I recommend as an approach. The basic idea is to start your modeling with the simplest version of something that approximates what you want to do, the simplest. Sometimes the simplest is not so simple. In this case, we're starting with this multiple server queue, and I hope that after yesterday, you can see that this basic idea is almost everywhere. It's ubiquitous. This idea of you have things that come in, and if the resources that are serving those are all busy, then you have to wait in line, or the fancy word for that, of course, is queue. And you then get served when it's your turn. Now we've dealt with the simplest possible version of that, and again we're going to reiterate using event graphs the simplest version of that. But the idea is that then what you do is you examine it for assumptions, and assumptions can be explicit. There are explicit assumptions such as the kinds of parameters and other things. And a lot of times there are kind of hidden assumptions. So there are some implicit assumptions that we're making, and it's important to uncover those. I also find it important to be very explicit, sometimes brutally so, about what the model is assuming and assuming away. Remember the mantra, all models are wrong. And that is true for every model, regardless of where it comes from. One of the challenges in the way that DoD acquires models like this is that they will typically acquire it from a contractor, and that's quite appropriate. The dilemma is that the contractor is in the business of making money. I mean, they're in the business of serving DoD, so again, this isn't to bash contractors, but they are a business and they need to make money. And they also will typically have marketing types that that extol the virtues of their product. That's what marketing is about. It's in part, saying how great our product is. There's very little incentive for those a commercial simulation to expose its weaknesses. And yet, from the modeler's standpoint, it is absolutely critical that these weaknesses, and by weakness, I mean the things that are not being modeled, that they be examined. So we're going to look at that in just a little bit of a case here. So we're going to dip our toes into that by taking our multiple server queue and examining it for these assumptions. And then we're going to find that there's one assumption which is violated in certain situations, and that has to do with what I'm calling finite waiting room here. So we'll get to those models. But first, event graphs. So what is an event graph? The idea, if you remember, that the key elements of a discrete event simulation model were the states. And the important thing about states were these state trajectories and these things called events, which have to do with the state transition. So remember, a state transition is an instantaneous change from one value to a next value. And that's something that we identify as an event. So what event graph methodology does is it represents the scheduling relationship between events as a graph. Now, the term graph may seem a little odd. Basically, in this setting, what we mean by a graph are nodes and arcs. Nodes are circles, arcs or edges are the arrows that are between them. So what event graphs do is they identify the node, that is the circle, with the state transition. Oops. Why? Change the color of my pen. Okay, so the node, the state transition is the event. So when we see a circle, that's what we think of as an event. And what an event means, in this case, is a state transition. That is an instantaneous change from one value to the other. But if you remember, in our description of the models yesterday, we needed a lot of verbiage to describe the relationship of the scheduling relationship between two events. And so what event graphs do is they represent that with these edges. So this is an edge right here, and an edge points from one node to another, that is from one event to another. So this is the sort of the canonical representation of the language, the basic language for event graphs. And there are several pieces to this. The first piece, of course, are the two events. So we have event A and event B, and we draw those as circles. The second element is this edge, and the edge is a scheduling relationship. And it says A has a scheduling relationship with B. And it's a directional one, meaning that in this case, A will schedule B, but A may schedule B. So there are two attributes of this scheduling edge. One is this, what's represented as an I with a little squiggly under it. That's just sort of how things were done by the guy who invented these, who wasn't me, by the way. So what that is a Boolean condition. And that's either true or false. So that's what Booleans are. They're either true or they're false. And the idea is that if the condition is true, then the scheduling edge takes place. That is, if condition I is true when A occurs, then event B will be scheduled. That is, it'll simply be put on the event list. Now, the second attribute of the edge is this value T, What T is T is the delay from when event A occurred until when event B occurred. Okay, so that's an important thing to remember. In other words, when A occurs, assuming this condition is true, then event B is going to get scheduled T time units later, not at time T, but T time units from right now. Okay, and that's the whole thing, that, or at least in its most basic form. Now, after we've worked with these for a little bit, we're going to add just a couple of more little tweaks to this, but only a few, only a handful. But just with this, we can model, we can represent what we did yesterday. And these are the 4 steps in defining an event graph model. So first, as before, we define the parameters. Remember, the parameters are the variables that don't change. Second, we define state variables. Those are the values that do change, and with the caveat that they change instantaneously by jumping from one value to the next. That's what are called state transitions. When you're defining state variables, this is important to include the initial values. So whenever we define a state, it is not enough to simply define, say that n is going to be the number of arrivals. We have to also say that initially, when the simulation starts, the value of n is going to be 0 in this particular case. Okay, so we've defined our parameters, we defined our state variables, and now the next step, and this steps 3 and 4 are ones that, you'll hear me kind of harangue about this a bit. And some of you will simply ignore it, and that's okay. You don't get marked down for ignoring it, but but it's important, or at least I found it to be extremely useful, to first write down all of your events. In other words, identify all of your state transition and write them as events. That is, try to sit down and figure out, okay, what are all the possible changes, state transitions, that each state variable can make? And for each of those, write that as an event. And do that before you try to draw any arrows. And then only when you've written all of the events do you identify the scheduling relationships and write those as edges, that is, arrows between one event and the other. Okay, so sounds simple, and it is, but the caveat on simple is that simple is not always easy. Okay, so let's look at our arrival process. Now we've pretty much, this is the same model we did yesterday. That's the idea is that we have some event that just sort of periodically occurs. We call that an arrival, but calling it an arrival doesn't really make it an arrival. What makes it critical are these state transitions. What makes an arrival is the fact that it increments our state variable n. And so our parameters, again, are our inter-arrival times, that is this whole sequence. And our state variable, we're going to call it n, and our initial value is going to be 0. Typically, this is, instead of writing all this out, I would often say something like n and then put the initial value in parentheses, something like that. That's perfectly fine. As long as the initial value is there, the initial value has to be there. If I ask you to define an event graph model and you define your state and do not give an initial value, then it'll be marked down. Define the state transitions. Again, we had 2. One is the initial is always a state transition, and that always goes in the run event, and that is that we start with none. And then upon an arrival event, we will, or what we're calling an arrival event, and you can call it whatever you want, just don't call it late for dinner. But the arrival label is not important. What's important is this state transition. Okay, and what I'm going to do now is, and it's on the slides, but what I'm going to do now is first, oops, a question. Yeah.
So is this similar to like a finite state machine? Like would it be coded the same way?
Yeah, good question. In short, absolutely not. um, it looks like a finite state machine because a finite state machine has circles and arrows like this. It is completely different. So do not apply, when you're doing event graphs, my recommendation is you take everything you know about finite state machines and you kind of put it aside where you can find it again. Okay, so what I'm going to do is I want to show you how you can be doing this. And again, so we start with a blank sheet, basically. And in this case, we've already defined, oops, I don't want red. I want blue. Okay, so we've already defined our inter-arrival times and our n are, okay, so we've defined that. Now, when you're defining one of these event graph models, the next step is to identify your state transitions. There's one you can always start with, and that is if you have completely defined your state variables, including the initial value, then you can always write down one event, and that is the run event. And it looks like this. You simply write run, put a circle around it, and then in the state transition, which goes under the event node, and I typically put it in curly braces, but as long as it's clear what it is, you simply write the value, the initial value or values that you get from defining your state variable. You can always start with this. Now, the next thing is to look at all of your state transitions, or if you haven't already, you look at your state variable and simply ask the question under what are the possible changes of value that this state variable can have. So I look at n, and n is simply the number of arrivals. And since my arrivals are coming one at a time, the only state transition that it has is to increase by 1. And so that we're calling that an arrival. Again, you can call it anything you want, but it is recommended to call it arrival in this particular case, just to be consistent with everything else that's being done. Okay, now notice I have drawn the nodes first. I've drawn the nodes first. And then I want to look and say, is there anything that I've forgotten? Is there a state transition? Is there a possible change of value of this state that I haven't thought of? And the answer is no, I haven't thought of it. Now, that doesn't mean there isn't one. It just means I haven't thought of it. In this case, I don't think there's any. Okay, so then, and only then, you start looking at the scheduling relationships. So when we start with the run, we need to schedule that first arrival, and we're going to schedule it after a delay of time t sub a. Now, there are actually a couple of schools of thought on this. One possibility is sometimes they just have the arrival come immediately at time 0. I generally prefer to do it this way. So that's the way you're going to do it as well. But just know that this is kind of arbitrary, but this next one is not. So every time there's an arrival, it schedules the next arrival. So basically a guy shows up, and then as far as the model goes, it says, okay, how much time until the next arrival? Again, not when does the next arrival come, what is the time until the next arrival? That's what these T sub A's are. They are inter-arrival times. And that is done by in this case, a self-scheduling edge, because arrival schedules another arrival. Okay, so, and then that's it. We're done. This is the model. This is the event graph model. And if we see, if we move forward here, we see again, this is kind of what I did, and this is where we landed. Okay, so what I hope you appreciate about this, and if you don't, then that's okay too, is that this is a complete model. You know, this together with the definitions is a complete model. What's different about it than what we did yesterday is that when you look at this, especially if you understand what these means, the structure of this model and how it behaves is much more clear. That is, we see that we start off with scheduling that first arrival, and then this self-scheduling edge simply says, okay, this arrival is just going to kind of keep these guys coming.
So that is, you said what we did yesterday. This
is exactly what we did yesterday.
That's what I was envisioning.
Yeah, the difference is that this is much easier to look at and see what's going on. Okay, so that's the simple one. Now, okay, and there's our final model. The final model consists of these three elements: define all the parameters, define all the state variables, and then write the event graph. And the event graph has its state transitions identified with the nodes and the scheduling relationships between them. Okay, so that's what a model looks like. Okay, so let's look at the multiple server queue. That's the second one that we did yesterday. So again, we had parameters. We had three parameters. We had our inter-arrival times, we had our service times, and we had the number of servers. Now for state variables, we had Q, the number of customers in the queue, initially 0. We had the number of available servers, which was initially K, and then L, the number in the system, which was initially 0. And for this model, I'm going to, this isn't always the best idea, but this is something which is possible. I'm going to explicitly include this L, the number in the system. That is redundant, but I'm doing this just to illustrate the fact that, so even though, when I say redundant, this relationship, what I'm writing here, between L, Q, K, and S, this always holds. That is the number, if you tell me Q and S, the number in the queue, the number in the system, and I know how many total servers there are, K, then I always know what L is. But nevertheless, just to illustrate that we can sometimes have an over described model, I'm going to include L just to be ornery. Okay, so it isn't strictly speaking necessary, but we're going to do it anyway. So now our state transitions, again, this is the only difference here is the L state transition. So we need to look at what that is. So initially Q is 0, S is K, and L is 0. Where did that come from? That came directly from our definition of the state variables. So I can always write this one down if I've defined my state variables correctly. So now this had an event called arrival. It was the same as name as the arrival process one, but it meant something entirely different. In that case, Q was incremented by 1. And in this case, we now have one more guy in the system than we had before. Our others are, we started service, which meant that we took a guy away from the queue. We took a guy, one of the available servers away. And then finally, at the end service event, what we're calling the end service event, we have one more available servers, and then we have one fewer customer in the system. Okay, so now let's look at how we would formulate this. And again, I'm doing it on the whiteboard here to give you a sense of how you can be doing it from a blank sheet. I mean, the thing about these modeling can be challenging. And, you know, as you may guess, it's in a very short while, you're going to be asked to do this from a word problem. So you're going to have a word problem, and you say, formulate an event graph based upon this description. Okay, so this is the kind of thing you're going to want to do, and that's why I'm doing it on the whiteboard. I mean, the PowerPoint has it just for, you know, record's sake, but the PowerPoint doesn't give you the full Monty in terms of how to deal with this. So again, what are our state variables? We had Q, we had N. No, we did not have N. We had Q, we had S, and we had L. Those are our state variables. Okay, so we always have run. So what was run? Run will take each state variable and set it to its initial value. Now I can always write this down if I have defined my states, because remember, a state is not fully defined if it does not include its initial value. So if I fully define my states, then I can always write this down. Okay, now comes the hard part. I have to look at each state variable and say, okay, what's the state transition that could happen for it? So again, we did this yesterday. So we had an event that we called arrival, and that's when Q increased by 1. And pardon my writing here. All right, so Q increased by 1, but also because we included our L here, the number in the system is also going to increase by 1. Then we have, okay, now what happens when Q goes down by 1? Well, that's when they start service. So that's an event we called start service. And its state transition was, we took a guy out of the queue, and we took an available server out of the pool of available servers. And then finally, we had an end service event where we put a server back in. And then now, again, because we also have this L, that's when we have 1 less in the system. Okay, so this is not pretty, as you can see. This is why when you do this, you should do it in pencil and have a very large eraser. Okay, so again, notice I have done all of the events. I've written all of the events first. And now that I have all of my nodes, all of my events, I can look at what is the scheduling relationship. So again, the first arrival is going to appear after T sub 8 time units, and the next guy is going to show up another T sub 8 time units later. Again, remember, the thing to understand is that even though, see, I got a T sub A here and a T sub A here, they're typically not going to be the same values. What this means in event graphies is that because this was given as a sequence, whenever I encounter that variable, I simply pick off the next value in the sequence. When we start doing this on the computer, this will almost always be a random variable that's being generated. And we'll talk more about that when we get to implementing them. Okay, so now the arrival may schedule a start service event, but remember that Boolean condition we had. So here's the Boolean condition is that S is bigger than 0. In other words, an arrival to the system can go right from the queue to start service, but only if there's an available server. If there isn't, then nothing happens. And the thing to also remember is that if an arrival event occurs and it cannot schedule a start service immediately, then it does not, I repeat, does not sit there waiting for that to happen. Now, if you're a customer, you sit in the queue waiting for that to happen, but the event does not. The event one occurrence of the arrival event has one shot, and only one shot, to schedule start service. If it can't do it, then too bad, too sad. Its opportunity is gone.
On the in-service yesterday, I don't remember us doing L equals L minus 1. Is that intentionally different? I'm not seeing it in the slides from yesterday.
Yes, it's intentionally different. I just added an extra state variable to the one today. It's just an extra state variable. So everything else is the same. So if you want to just ignore the L's, you can ignore them.
I was about to start redoing my homework.
Okay, so now when we start service, we schedule end service. Now T sub S time units later. What's T sub S? That was the service time. So that says when we start, we're going to have to do for a certain amount of time. And that's going to be different than the inter-arrival time. So if customers are coming on an average every 10 minutes, and our service time may have an average of every 7 minutes, or may have an average of 20 minutes or more, depending on what the service is. But that always happens. And then finally, when the end service event occurs, then we now have an additional server. And if there's somebody waiting in the queue, then you want them to be doing that. And so the condition, we will only do that if Q is bigger than 0. In other words, if there's somebody waiting in the queue when we finish service on a customer, then we will schedule another start service event. And as messy as this is, the procedure that I am suggesting is that you get a pencil, big eraser, you sort of sit with doing this until you get it right, and then you maybe copy it over in a neat manner for turning in. So when you turn it in, try to turn it in a little more neatly than I've done here. So, but this is the recommended approach. And if we go back, and this is all in the PowerPoint as well. So if we take a look at what's going on here, again, I write the state transitions in a neater way because I can do it more neatly on the computer. So we write the state transitions as events. We identify the scheduling relationships. And again, this is not, how should I say, this you can do, but all you need to, when I ask you to do these, all you need is this. That is, you don't need this. You don't need to turn this in, as it were. This right here says it all.
So Professor Buss, when we draw these event graphs, we will draw the arrows?
Oh, absolutely, yeah.
Okay, thank you.
Okay, so let me get back to where I was. Where was I? Where'd you go? Okay, so our final, so here's our final model. This is the kind of thing that that you would turn in. So, something like this. It doesn't have to look exactly like this, but parameters, state variables, an event graph. So this is a complete model. And again, this L, as you were pointing out, I put this in today just to illustrate the fact that there's not necessarily one and only one right answer to these. These are kind of arbitrary. And this model is exactly the same as yesterday's model, only it has one more state variable. So it does exactly the same thing. so let me, where are we here? All right, so now for some of the fun part. Okay, so here's our multiple server queue model. And now and this is important in the modeling process. It's a little less important in this class, but what I'm hoping to get across to you is the idea of modeling as an iterative process. And since all models are wrong, in a way, the modeling is never completely done. So there are some assumptions, and some of them hidden. In fact, the very first assumption is kind of a hidden one. And that is something called an infinite calling population. What does that mean? What that is a consequence of is the fact that the arrival rate basically remains constant no matter how many are in the system. So we're currently located, at least most of us, on the Monterey Peninsula. And on the Monterey Peninsula, there are roughly 100 or so thousand people. So let's say I'm modeling the Safeway on Fremont Avenue. And in my model, I can have as many customers in there as I want. And if I'm not careful about how I've defined it, it could be that I have something like 100,000 customers in my Safeway model. In this multiple server queue model, there is no constraint on that. There is no limit to how many I have in my queue. In other words, infinite waiting room is one of the implicit assumptions of this. Why? Because this state transition right here, Q plus one, it's not, okay, if we run out of room, you can't come in. Okay, so that the model assumes that. And that's a pretty good assumption in many situations. In others, it's not so good. And at some point, we're going to see a concrete example of a situation where that's not so good. Actually here, if I'm modeling Safeway on Fremont Avenue, the infinite calling population is actually a pretty good one. Why? Because no matter how many people are in Safeway, and I'm not sure what the capacity is, I don't know, 50, 100, as a fraction of the 100,000 potential customers on the peninsula, it's still, it's just a drop in the bucket. So even if I have 100 people in my system, it's not going to affect the arrival rate in any appreciable way. So that's a reasonable assumption. Now, let's say I'm modeling something like maintenance for carriers. Okay, now there are only like 11 of those in the world. So if for some reason 3 of the carriers are in maintenance, then that's going to appreciably affect the arrival rate to the system. And if my model doesn't take that into account, I could find myself in a situation where even though I have only 11 carriers, I'm currently maintaining 20 of them. Okay, that the model doesn't know or care about that. So okay, so those are some of the assumptions. Here's another assumption: all arriving customers join the system. So if a customer shows up, they're going to join. And furthermore, once they join the system, we got them. They're stuck. So the idea is that we need to examine these. And we take a look at our system, we take a look at our model, and we try to match those with the assumptions and look at any places where there may be a significant disparity between what we are assuming and what our model is saying. Okay, yeah, so I stand corrected. Yeah, I was talking about US carriers. Are there any other that really count? Yeah, I know. Okay, so yeah, US carriers, you're absolutely right. Okay, so here's what we're going to look at. I'm going to look at this assumption. The assumption is going to be the infinite amount of waiting room. So I look at my system and I notice that there's only a finite amount of waiting room here. I don't, if you're familiar with the in and out on Delray Boulevard,
Very familiar.
you'll notice that there's, for the drive-in, there's only a finite amount of waiting room. Now they kind of they kind of tend to violate that at times when they kind of pour out, but even in the overflow, there's only a certain amount of waiting room there. So we look at that, or we there might be the waiting room of some facility, and that it's actually there are only a certain number of rooms. And especially in, with today's COVID, they say, well, we can only operate at X% of our capacity in the indoors. And so what that means is that if somebody shows up and there's no room at the inn, then what happens? So what we observe for the system that we're looking at. So basically I drive up, with my mouth watering for a double animal style. And I come up and then the line is right out to the road. There's no room. And being a good citizen when it comes to driving, I'm not going to sit there and block the road like some of these other jerks. So what do? Well, I'm gonna just basically go away. I mean, it's so when we observe the system, we notice that potential customers will leave before entering the system. Okay, so we observe that, and our system, our multiple server queue does not do that. That's the important thing. Our multiple server queue does not do that. The technical term for that in queuing is called bulking. It's not the same thing as making a motion towards first without actually doing it. That's an entirely different kind of bulking. So, but let's model that. So we're going to take our basic multiple server queue model, and we're going to have to add some stuff to it and modify it. So the first thing is we're going to have to add a parameter. We're going to add a parameter that's the capacity of the waiting room. Okay, in and out it will be, we count how many cars can there be in that until it reaches the road. And I wish, I think as somebody pointed out, it is really a bad thing when people start kind of waiting in the roadway for that. But that's we'll pretend that we have nothing but good citizens and they're doing that. And so now what might we be interested in? If you're running this facility, one of the things that you'd be interested in is what percentage of customers do we lose by this? And so for that, we're going to add two more state variables. One is going to be the number of potential customers, which again we're going to initially be 0. And then I'll call it B, the number of lost customers, or bulks, as it were. B for bulk. Okay, so it's just like the others. So in addition to our multiple server queue model, our run event is going to have to initialize N and B to 0. Arrival is now, arrival is only going to increment the N, and we're going to have to add another event, which is where I'm going to call join the queue. And it's going to have the state transition queue as Q plus 1. So remember we had that, what we were calling L. L is now history. We're not going to have L in this particular one. And then the other is we want to count the number of bulks. So we're going to have an event called bulk, and that's going to increment our state variable B. And then we're going to have start service and end service pretty much as before. Okay, so now looking at the time here, I only have a few minutes to do this, so I'm just going to do it with the PowerPoint here rather than doing it out by hand. But again, the first thing is to write our state transitions as events, and it would be really in a, oh, and it looks like I did put L in, so I'd better. Okay, so, but again, the principle is that we want to write our state transitions as events before we do anything. So we have run, which initializes our state variables. We have arrival, which now only increments now this is a little more like our arrival process, because now we're saying, okay, we now have one more potential customer. And when we join the queue, that's a separate event now. So we're going to increment Q, we're going to increment L because because start service and end service are going to be exactly the same as before. And now here's this additional event, bulk, which is going to count the number of bulks. All right. So then when we write the scheduling relationships as edges, this should all, okay, let's look at what's the same. Okay, this is the same. This is the same. This part is the same, like all of this stuff over here. Once we get into the system, this is all pretty much the same. However, let's pick another color. Oh, let's do green. All right, so now what's different? Okay, let's look at the arrival event here. There are two possibilities. Either there's room at the inn, and how do I know if there's room at the inn? Because Q, the number in the queue, if that's strictly less than the capacity, then that means there's room for me to join the queue. On the other hand, if my queue is at capacity, then I'm just going to balk and leave the system. And after I've run this simulation, I can find out how many I've lost by looking at this value B over N. Okay, but what's the same and what's different? Again, the arrival stuff is all the same. Once I join the queue and I start service and end service, that's all the same as before. It's all this stuff in here that's different. Okay, that's all it took. And this is partly why it's always useful to do it incrementally. So given that I had my multiple server queue model to begin with, this one, I can now easily just add the additional ones here. And then, okay, so our time is up a little bit, but then it turns out that this model is going to have a little bit of a problem if, in fact, I don't have any room at all. In other words, look at this. What if C is equal to 0? In other words, what if I have no capacity whatsoever? Well, this model will not work because this will always be false. So if there's no Q, if there's no the QUEUE, then there's no need for a state variable Q. And so I actually have a much simpler one. And that is if I show up, if I arrive, then I can start service, but only if a server is available. And otherwise, I'm going to balk. Okay. So that's another thing, just to be you need to be very careful of this. So here, this was another implicit assumption that capacity, and I think I was explicit about that. Yeah, notice I was explicit. I said capacity has to be bigger than 0. But then you say, well, what if capacity is 0? You can ask your grandparents about this, but in the old days, before they had call waiting, if you made a phone call and the guy on the other end was on the phone You just got a busy signal. There was no call waiting. That didn't exist. So this model would be a better representation of that. This model could be a representation of the way things work right now.